Hello, this is Dr. David Lubkeman. In this video, we explore how to use a generative AI tool to create a Python-based 3-bus power flow program. We start by reviewing the circuit models and equations for a multi-bus power system with a single generation source. Then a series of examples using ChatGPT are used to demonstrate how to build the various power flow program functions. This includes how to organize the program functions, how to write input requirements for each function, and what is involved in debugging the generative AI developed code. Before we start in on the coding, I'm going to review the power flow model and the associated equations for the 3-bus system shown here. This is a balanced 3-phase power system consisting of a single generation source and constant power bus loads. The source is assumed to be ideal with a constant voltage and frequency. Each transmission line is to be modeled by a series resistance and reactance, as well as a shunt charging capacitance. The buses have 3-phase loads with real and reactive power components. The impact of additional generators will be the subject of a future video. Based on the data associated with the generation source, line segments, and loads, then we can perform a power flow calculation. The basic power flow algorithm gives us the load bus voltages. From the bus voltages, we then compute line flow real and reactive powers. Finally, losses are calculated using the line power flows. Power flow analysis calculations are based on a per-phase model as shown here. A per-phase model represents a single phase of a balanced 3-phase circuit, where phase voltage magnitude is related to line voltage magnitude by a factor of a square root of 3. The source is modeled as an ideal voltage source. Line segments have a series resistance and reactance, as well as a shunt charging capacitance. And we will be using a pi equivalent line model where we lump half the capacitance at the end of each line. Loads are represented by constant real and reactive power consumption, where for analysis we used a per-phase model, which is 1/3 the 3-phase consumption. The bus voltage formulas are based on Kirchhoff current law equations written at each bus. So the sum of the line currents exiting that bus is equal to the injected load current. For example, at bus 2, shown here, we express line current in terms of the bus voltages in order to get I line 1-2, I cap 1-2, I line 3-2, and I cap 2-3. The injected current is found by taking minus the conjugate of S2 divided by V2. The minus sign is due to the fact that we want an injected current, which is minus the load current. We go through a similar process for bus 3. If we take these Kirchhoff law equations and combine coefficients for the voltage, we can then rewrite the equations in terms of admittance coefficients denoted by Yij. We can see that there is a pattern associated with these admittance terms. In the case where I is not equal to j, then the admittance is negative the inverse of line impedance Zij. So for example, Y21 is negative the inverse of Z12. In the case where I is equal to j, the admittance is the summation of the line and capacitive admittances. So for example, Y22 is the sum of admittances for elements connected directly to bus 2. Note that on the right side of the equality that we have a bus injection current. In the case of constant power loads, this is minus the conjugate of load power divided by the load voltage. Since this injected current is inversely proportional to voltage, then what we have here is a nonlinear set of equations. The individual bus equation admittance terms are stored in a matrix we refer to as Ybus. We can easily formulate the diagonal and off-diagonal terms through applying the Ybus building rules discussed in the previous slide. In matrix form, we then have Ybus times V equal to I, where for an n-bus system, Ybus is dimensioned n by n, and V and I are the voltage and current matrices dimensioned n by 1. The current injection matrix is populated with the bus current injections based on load values as shown in the previous slide. So given that we know Ybus and I, we then need to solve these matrix equations for V. To solve for the unknown voltages for our 3-bus system, we start with the two equations with unknowns V2 and V3. Note V1 is fixed at the ideal source voltage. Using estimates of I2 and I3, we could solve for V2 and V3 by using a Python matrix solution library. However, in this presentation, we will use an iterative solution technique referred to as Gauss-Seidel. In this approach, we calculate the voltage terms one by one instead of solving a system of matrix equations. We first update V2 based on estimates for I2 and V3. Next, we update V3 based on the estimate for I3 and the last calculated value for V2. By iterating between these two equations and updating I2 and I3 after each iteration as well, then we will eventually converge to a final solution. Let's take a look at a flowchart for implementing the 3-bus case in code. To solve for voltages using a Gauss-Seidel approach, we start out with an estimate for the unknown bus voltages. We typically use either the source voltage or a rated system voltage. Next, we compute the Ybus entries using the Ybus building rule. Since this is an iterative technique, we need to repeat the solution process until the voltages converge to within a tolerance. This status will be tracked with a convergence flag that is initialized to true. We first obtain an update for V2. Note that the current I2 is minus a conjugate of single-phase bus power divided by phase voltage. We then check to see how much V2 has changed. If the change is greater than an error tolerance factor, we set the convergence flag to false. We then update our voltage matrix with the updated value for V2. Then we solve for an update for V3. Again, we check to see if the change for this voltage is within the error tolerance and set the convergence flag to false if the test fails. We then update the voltage matrix with the updated value for V3. If either convergence test has failed, then we go back to step 3 and repeat the process until a convergence is finally achieved. This flowchart can then be generalized for a multi-bus system with n buses as shown here. We simply need to set up a loop to iterate over each load bus, which is not the source bus, bus 1 in this case. The voltage update formula makes use of a summation over the appropriate Y times V entries. This is the algorithm which we will want to implement in our Python PowerFlow example. Once the bus voltages are calculated, then it is possible to compute line power flows and losses. This figure shows how to get sending and receiving end power flows into the line segments. Note, since we have line charging capacitance, that this capacitance needs to be factored into the line current calculation as shown here. Line losses can then be computed by adding up the sending and receiving end power flows. To find the power injected by the swing bus generator at bus 1, we need to realize that the bus 1 current computed by taking Y bus times V is actually a net injected current. This net injected current I1 will be equal to I gen 1 minus I load 1 as shown in this figure. To find S gen 1, we can use the formula shown here where we compute 3V1 times I1 conjugated and then add the swing bus load power. We will test our program code using the 3-bus case shown here. Note bus type SW denotes a swing bus, which is an ideal voltage source. PQ denotes a load bus. The bus voltage field represents the rated voltage. The line charging capacitance is given in terms of nanofarads. The solution for this 3-bus power system is shown here. These results were obtained by using a pre-existing PowerFlow program. In this first example, we will ask the AI tool to create a Python PowerFlow for a 3-bus power system. The first part of this request is focused on describing the bus and line data. Note we are providing system data in tables using Jupyter Notebook markdown format. Next, we append a set of general program requirements. These are general in the sense that we specify a Gauss-Seidel algorithm based on per-phase modeling. However, we do not provide a program flowchart or many algorithm details. The program outputs required are given in the very last section. In these examples, we will be using ChatGPT as a generative AI tool. The program request is entered into the browser chat box as shown here. The response provided by ChatGPT starts out with a brief explanatory text on the coding steps. The program code is in a separate screen, which can be copied and pasted into a Python environment. Let's see what happens when we copy this Python code into a Jupyter Lab cell and execute it. You can use any Python environment to test this code. In this presentation, I am using Jupyter Lab since it provides me with a means for capturing and documenting our coding examples. The video description includes a link for you to download this code. When we browse through this code, we see it begins with the import of the needed Python libraries. Then global constants used throughout the program are defined. Next, the data case we provided is represented as two Python data structures, one for bus data and another for line data. At this stage, I don't want to spend any time analyzing this particular code for correctness. The comment suggests, though, there is a Gauss-Seidel iteration loop, and we have the printing of results at the end. When we hit Shift-Enter to execute this code, we see that it runs without syntax errors. Unfortunately, we get the wrong answers. The answer gives a rise in voltage at buses 2 and 3, where typically under loaded conditions, we should see a voltage drop. Also, the line flows are much smaller than the bus loads. So even without having the benchmark results, we can see that there are issues with this code. Rather than trying to modify this first attempt, let us repeat our ChatGPT request using the exact same query. Now we get a different result. A generative AI engine such as ChatGPT utilizes probabilistic algorithms, so you don't get the same results with the second query. When we hit Shift-Enter to execute this second attempt, we see that we now have syntax errors in the code. If I repeat this process a third, fourth, fifth time, etc., I will get similar results. When using generative AI to produce code, we typically do not get a correctly working program from a general query, like used in this example. Even though the code might look okay, there will be either errors in logic or errors in code syntax. So one needs to be prepared to do extensive debugging to get code based on general requirements, as I have tried here, to execute and produce correct answers. A better approach to using AI to develop a power system analysis power flow program would be to break the development into smaller steps. So instead of asking for the entire power flow program, we break our effort into developing a small piece at a time. That way we can focus on writing more specific requirements and debugging each code module in a more manageable fashion. In this approach, we start with defining a main program that calls the various power flow functions. We start with defining an appropriate data structure. Then we develop a plan for the functions we will need, which will then be specified and developed one at a time. Let's take a look at how we can improve on our first example. We will develop our power flow using the framework shown here. We start by defining our global variables. Then from the main program, we call our various functions. Our first function call is to set up a bus and line data structure. Next, we build a Ybus admittance matrix based on the line data. A Gauss-Seidel algorithm is then used to compute the bus voltages. Once we have the voltages, then we can compute other output variables such as line flow, total loss, and generation power injection. Finally, we print the results. Earlier in this presentation, when we requested PowerFlow code in attempts 1 and 2, ChatGPT returned two different data structure suggestions. I am just showing the line data structure for the sake of comparison. The first attempt suggested that the entries be stored using a list structure with each entry in dictionary format. The second attempt contained a list structure as well, but with entries in Python tuple format. There are many different ways this data can be represented, and it is important to identify the best structure for our particular application before getting started with writing code. One way of approaching the data structure selection would be to first ask the AI tool to identify possible options. Here we see a query designed to do just this, based on our bus and line data, which is included in Jupyter table format. In this case, we get 4 recommendations with sample code given for each approach. We will use list of dictionaries, option 2, since we are working with a simple and small data set. For the case list of dictionaries, ChatGPT provided us with the sample code for the data structure. So once we have tested this in Jupyter Lab to make sure it works, we can then use this directly in our input function. The first function we will develop is input data, which creates both bus data and line data structures and passes these back to the main program. Shown here is the request we make to our AI tool, where we simply ask to build and return the data fields defined in our earlier query on data structure options. We would normally get our raw bus and line data from a data file, as opposed to having it fixed within the program code. But how to do this will be the subject of a future video. Based on this query, then ChatGPT returns the requested code for the input data function. We then copy and paste this code into our template for the main program. Shown here is the developed code inserted into a Jupyter Lab cell for test purposes. You can see that we are using print statements in our main program to make sure the input function is properly working. The next function to be developed is Ybus Build, which constructs a bus admittance matrix based on the line data. We will set up the request assuming that ChatGPT has already been trained on power system code that utilizes Ybus building. This is a safe assumption given that this is a common element of power system analysis programs. I also append the code that has already been developed to this point so that any dependencies as far as variable naming can be accommodated. The response includes a description of the algorithm as well as the updated Python code with the new function added. Next, we paste the updated code with Ybus Build into a Jupyter Notebook cell in order to test it. Again, we use print statements in the main program to view selected entries. We do not get any syntax errors, but at this point we don't know if the Ybus entries are accurate. So our next step is to test print Ybus entries to those generated by manually computing Ybus entries in a second cell. We see that our selected entries match up. Once we have a data structure and a Ybus Matrix function, then we can define the Gauss-Seidel function. In the AI tool request shown here, we define the program inputs and output, then provide details on requirements. Again, I am assuming that PowerFlow Gauss-Seidel algorithms are included in the AI tool training set. The requirements include the use of the tolerance and max iterations global variables to control the iterative process. As before, we asked ChatGPT to add this function to the code developed so far. Note that the ChatGPT session actually remembers the last code section, so it is not necessary to append it in this case, but I'm doing it this way in case you want to replicate a standalone piece of this example. The Gauss-Seidel response includes a short description of the algorithm plus the updated program code. After pasting this updated code into a Jupyter Lab cell, we can take a closer look at the code and test it. From a first glance, the Gauss-Seidel algorithm appears to be complete. Although the code does execute though, it does not give correct results according to our benchmark. So obviously there are logic errors we need to fix. The code is also lacking the angles on voltages, so this needs to be added for debugging purposes. We can ask ChatGPT how to modify the code to include voltage angles as shown here. Then we add the response to our code base before debugging. As we go through the latest version of this code, we can see a number of small problems that need to be fixed. At the beginning of the program code, the tolerance factor has been set to 1e⁻⁶, or 0.0001%, which is a factor of 100 smaller than we requested. So change 1 is to reset this back to 1e⁻⁴. I will simply comment out the original code and add a new line with the correct tolerance factor. Next, at the beginning of the function, we need to initialize the bus voltages. The swing bus voltage is set to the correct value. However, the other bus voltages are initialized to 1 per unit, even though we are not working in per unit quantities. To fix this, change 2 is to break this into 2 parts. First, I find the swing bus reference voltage from the bus data structure. Then I use a second for loop to set all bus voltages equal to this reference value. This is sometimes referred to as a flat start. As I move down the code into the iteration loop, I see that the bus load powers are being set. There should be a factor of 3 to convert 3-phase to single-phase power, so change 3 is to change the divider square root of 3 to 3. Next, where the bus voltages are being updated, S load needs to be the conjugate of an injected bus power. The values in the bus tables are load powers. So change 4 is to invert the sign on the load power. Right after this code section, the error is computed. In the original code, the error is just the change in voltage, but it is not normalized. This would work if we were working in per unit, but this is not the case. So change 5 is to compute a normalized error term by dividing by V new. The last change, change 6, is to add degrees to the voltage printout. I have also adjusted the number of significant figures on the voltage magnitude. After making these changes, we see that the program converges to the correct result from our benchmark within 7 iterations. In this particular case, the changes needed were relatively minor. However, this example shows that you still need to be familiar with the algorithm and the power system modeling in order to catch these types of errors. Finally, once we have the bus voltages, we can start working on the output functions needed to compute line flows, losses, generator injection, as well as print results. In this case, we just specify the inputs and outputs to each of these 4 functions as shown here, and hope ChatGPT can provide the formulas. As seen before, after we submit our request, ChatGPT adds the new functions to the power flow code we have developed up to this point. Once we paste the updated code into a Jupyter Lab cell, we can take a closer look at it. It appears it has returned the functions as requested. However, when we execute the code, we find that we get incorrect results. Comparing these results to our benchmark, we first see that the power flows for the lines are low by a factor of about 3. Also looking at reactive power for the line flows, it does not appear as if charging capacitance has been properly factored in. The line power losses are also way too high. Finally, generator injection is too low by about a factor of 3. So obviously we have some debugging left to do. In order to debug the code, we need to know the formulas for the output functions. Fortunately, we have the equations as shown on an earlier slide that could be utilized for debugging. Let us start with the line flow function. We are iterating over each line segment. We will need the series impedance and shunt capacitance for each line segment. So change 1 will be to comment out obtaining this information from the Ybus matrix and accessing Z-line and Y-cap directly from the line data structure. To get Y-cap, we need to multiply capacitance in farads by 2 times pi times the frequency. So we need to account for whether we have a 50 or 60 Hz system. Moving down to the calculation of line current, we see that the old expression for sending end current did not factor in the line charging capacitance. So change 2 is to include Y-cap in the I from to variable, that is a current from one side to the other side. Following this segment in the calculation of power, then change 3 is to multiply by 3 to convert single phase to 3-phase power. Change 2 and 3 are also applied to receiving end power calculations for the line. At the end of the line flow function, the power values are added to a line flow list. Moving into the loss calculation function, since the line power flows are both into the line, then to get losses, we need to add these two terms together. So change 4 is to add instead of subtract these two terms. Next, in the generator injection function, we see that the swing bus load has not been included in the S-swing variable. So change 5 is to obtain the swing bus load value from the bus data structure and make sure it is in units of watts and bars. Then for change 6, we need to make sure that Ybus times Vbus is multiplied by a factor of 3 to get a 3-phase power, and then we add swing bus load in to get a correct value for S-swing. Once we have made all of these corrections, then when we run the code, we finally get the correct results after 7 iterations. In this presentation, I have shown how a generative AI tool such as ChatGPT can be leveraged to develop a simple multi-bus Python power flow program. In order to construct the power flow, we broke the development into smaller tasks. We started with a bus and line data structure as initialized by an input function. After this, we implemented an admittance matrix Ybus building algorithm. Then we used requirements to build a Gauss-Seidel power flow solution algorithm for determining the voltages. Finally, we developed output functions for taking the voltage solution and computing line flows, losses, and swing bus generator injection. Source code for the examples can be found at the GitHub site provided in the video description. This is available in both Jupyter Lab and Python standalone program format.